All right, hey Titans, Mr. Dresser back to do some more IM2. Today we're going to talk about indirect measurement using similar triangles, so similar to what we've been working on. Indirect measurement is a way that we can use proportions to calculate measurements that might be difficult for us to otherwise calculate. So we're going to indirectly find how tall something is or how wide something is. For example, it might be hard for us to go find the height of a tree because we might not be able to climb the tree, right? Something like that, or a tall building. We could also find the width of a river, right? That otherwise, if we tried to go calculate it, we'd get swept away by the current. So we can indirectly use some other measurements and use what we know about similar triangles and proportions to calculate those measurements. So we're actually going to go ahead and solve these problems. First one, let's go ahead and look at our person here. We're going to call that Manjad. Manjad is standing and he creates a shadow, right? He's got a shadow on the ground. And then the tree also has a shadow caused by the sun. And so what Manjad did was he went and stood so that his shadow ended right here, the same place where the tree's shadow ended. So the shadow of the tree is right here. It is 102 feet long. Manjad's shadow is right here. It is 17 feet long. We can measure those, right, with a tape measure or walk it out with your feet, something like that. And then we know that he is 6 feet tall. So we can now use these three measurements to find our unknown height, which is the height of the tree. The reason we can do this is we know that the two triangles that are formed, right, there's a triangle here formed by Manjad, and then there's the big triangle formed by the tree and its shadow. We know that those two triangles are similar. Why are those two triangles similar? Well, they're similar by angle, because this angle here, the one formed by the sun's rays and the shadow, is going to be the same for both triangles, right? That's the reflexive property using angles. But then also, Manjad is standing perpendicular to the ground, so that forms a 90-degree angle. And then the tree is growing straight up out of the ground, which also makes a 90-degree angle. So we do have similar triangles, which means we can write a proportion and solve it. So we could do something like taking the two heights, right, 6 over h, and setting it equal to the lengths of the two shadows, which since I started with Manjad's height, I'm going to start with Manjad's shadow. Right, so 17 would go first. And then the shadow of the big tree tells us the whole shadow was 102. And so now we can go ahead and cross multiply. So 17h equals 612 divided by 17. And this is where I grab my calculator. 612 divided by 17 is 36. Awesome. So I don't want to leave my answer as 36, because if I just say, hey, it's 36, 36 what, right? So we want to make sure we put our units on our answer. So in this case, we know that the height of the tree is 36 feet. So that tree is 36 feet tall. I do want to show an alternate way to set up your proportions, right? We could do height over height equals shadow over shadow and pick those corresponding sides. Or you can also do height over shadow of one triangle. So I'm going to do the height over shadow. So using two parts of the same triangle. So I could do his height is 6, his own shadow was 17. And then I can set that equal to the height and the shadow of the other triangle. Right? So the height is h, the shadow is 102. All right, so this first example I did the corresponding pieces. This time I'm doing two sides from the same triangle equal to the same two sides in the other triangle. But regardless of how I do it, I still get 17h equals 612, which that's the exact same thing we got with our other setup. So I still get the final answer is 36 feet. I'll probably go back and forth showing the two different ways to set up proportions. Find whichever way works best for you. Okay, here's another similar one, right? We've got a person standing here, we've got their shadow, we've got the tree, we've got the shadow. But this one says to be careful, right? So I'm going to make sure I'm careful on this. And I know the triangles are similar because of angle again, right? I got my reflexive property, and then I have my 90 degrees. But when I set this up, if I do height over shadow, so I'm going to do the two sides of the same triangle. I know the height of the person is 5 feet, and the length of the shadow is 6 feet. And so I'm going to compare that to the height and the shadow of the tree. Now the height of the tree is our unknown. And then how long is the shadow for the tree? That's right, on this one we don't know the whole length, but we do know that from the tree to the person it was 18 feet. And then from the person to the end of the shadow, it was another 6 feet. So altogether, the shadow of the tree was 24 feet long. So I'm going to put 24. All right, so we have to be careful. Were we given the whole length, or were we just given two parts of it that we need to add together? At this point, we can cross multiply. 6x equals 120. Divide by 6. X equals 20, which means the tree is 20 feet tall. All right, so it's basically what we've already done, just with a picture. It's not that difficult. You might have also noticed on here you can use the scale factor, because in order to go from 6 to 24, you would multiply by 4, which means to go from 5 to x, we're going to multiply by 4. And 5 times 4 is 20. Hey, look, same answer we got using proportions. All right, so we can use proportions or scale factor. Okay, here's another example of a shadow, but this time they're not standing in the same shadow. The person is standing over off to the side. Their shadow is not lining up with the lamp post shadow, but we can still use the exact same method. Because we can measure how high the person is, how tall they are. We can measure their shadow. We can definitely measure the shadow of the lamppost, which then allows us to find the measurement of the height of the lamppost. And the reason we know that these angles are the same is because the sun's rays are parallel, creating these two corresponding angles. All right, so let's go ahead and set this one up. I'm going to go ahead and do height over shadow again. So I'm going to do 5.25 over the length of the shadow, which was 6. And then I'm going to do the same thing for the second triangle. I'm going to do the height of the post over the length of the shadow. All right, you might notice that the scale factor here is 3, so we could just multiply this by 3 and get 15.75. I'm going to go ahead and cross multiply just because we're in the habit of doing that. It always works. But if you did notice the scale factor, you wouldn't have to cross multiply. You can do it either way. I get 94.5, divide by 6, and I get 15.75. So the height of the lamppost is 15.75 feet. Right? And again, I did height over shadow equals height over shadow. You could do height over height equals shadow over shadow, right? Or you could reverse that and do both of those backwards. As long as you do the same pattern and keep it consistent, you're going to get the same proportion in the end, and you will end up getting 15.75 feet. All right, so here's that river problem that we looked at earlier. We know that these triangles are similar because we have vertical angles, and then these distances were measured at a parallel section so that we were able to get alternate interior angles and also alternate interior angles there as well. So we know they're similar by angle. And so now when I go to solve this, I can do something like 20 over d So that's my parallel side over the side that goes to the vertical angle. And then I would do my parallel side first over here, which will then put the 45. So the 20 corresponded with the 36, the D corresponded with the 45, and then we can cross multiply. Which is 900 divided by 36. And I get that D equals 25, which in this case we're talking about meters. So the width of the river is 25 meters. Right. You could also maybe do 20 over 36 equals D over 45, right? Just another option. Okay, this picture looks a little crazy at first, but we have two sides of this triangle. So I'm actually going to go ahead and draw this triangle over here separately. We know that this side right here is 20 feet. We know this side right here is 16 feet. And then in the second triangle, draw that nice and big. We know that this side is a full 35. And we're asked to find the width of the widest part of the pond. So the pond goes from here to here. So we're finding this side of the pond. So now go ahead, take our information, and see if you can find the width across the pond. All right, let's see how you did. So one option for setting this up, I could do 16 over 20 equals, and then I can pick the corresponding sides of the other triangle, 35 over x. All right, that's just one of the ways we can set it up. If you set it up in such a way that you got 700 equals 16x, or 16x equals 700, then the way you set it up was great. It works. Divide by 16. And I get 43.75. So the widest part of the pond has a width of 43.75 feet. Definitely want to make sure we put those units on there. All right. So those ones, we'll have lots of problems like that. You can figure out the triangles are similar because of angle, and then we can set up our proportions. We've done problems like that. The one thing that's a little bit new that we're going to use is called the law of reflection. And the law of reflection states that the measure of an angle of incidence, which if this is a person looking down at a mirror, the angle that you look in at, right, or angle in, is going to be the same as the angle that it comes out at, or our angle of reflection. So these are not vertical angles, right? Vertical angle would be down here for this, but it is called the law of reflection, and we can use it anytime we're using mirrors. So why could this be useful for indirect measurement? Well, if we wanted to find the height of a flagpole or a building or a tree, again, right? We can do it with a mirror. So how do we know that these two triangles are similar? Well, he's standing at 90 degrees. The flagpole is at 90 degrees, right? They're both straight up and down. So there's one pair of angles. And then the second pair of angles, we just said this is called the law of reflection, right? So the angle that we're looking in at the mirror and the angle that we see bouncing off of the mirror will be the same angle. So they are similar by angle. And then physically, we can definitely measure the height of the person. We can measure the distance to the mirror, and then we can measure the distance from the mirror to the base of the flagpole, right? Those are all things we could take a tape measure or a ruler and calculate. But then the height of the flagpole would be a little bit harder, right? Someone would have to climb the flagpole, and that'd be dangerous, right? Maybe fun, but dangerous. So instead of doing that, we can just use our indirect measurement to solve for x. So we're going to go ahead and do this problem. All right. So the height of Mr. Dresser, from my eyes, right? Because my eyes are what look at the mirror. So not me, I'm 6'4", but my eyes are at a height of 6 feet. So we've got my eye height is 6 feet. I'm standing 8 feet away from the mirror. And then the distance from the mirror to the base of the flagpole is 24 feet. So if I measure those things out, I can now find the height of the flagpole. So again, I'd like to do the two sides within the triangle. So I'm going to do 6 over 8. So I did height over mirror length. And so now I'm going to match up the other triangle in the same order. So the height of the flagpole, I do not know. But I do know the distance from the mirror to the flagpole is 24 feet. And now I have everything I need to find the height of the flagpole. Cross multiply. 6 times 24, I'm just going to double check that. 144. Divide by 8. And x equals 18. So the height of the flagpole is 18 feet. Could you have done this an easier way? Absolutely. The scale factor from this triangle to this triangle was times 3. So if we did 6 times 3, we would get 18. Right? So sometimes the scale factor is an option as well. Okay, here's another similar problem. You are in Paris, France, and decide to use the mirror method, right? Because what else are you going to do in Paris, France, right? Than measure the Eiffel Tower with a mirror. But anyway, you're going to do that to calculate the height of the Eiffel Tower. We've got the measurements that we were able to calculate without having to climb the tower, and we can now find the height of the tower. So let's have you go ahead and try. Go ahead and take a minute, write a proportion, and see if you can find the height of the Eiffel Tower. And this is actually accurate. All right, so let's see how you did. One way we could set this up would be height over ground, right? The height over the ground distance, or distance to the mirror. So if we're looking at the Eiffel Tower, the height of the Eiffel Tower we don't know, but the distance on the ground from the mirror to the base of the Eiffel Tower was 1,700 feet. And we know that's going to be similar, or the same proportion, as the height of you, which you are 5 feet tall, whoever this you happens to be. And then the distance from the person to the mirror was only 13 feet. So based on this, we're able to cross multiply. 5 times 1,700, which is 8,500. And that equals 13x. Divide by 13. And the height of the Eiffel Tower is, hold on. This might not be accurate, but anyway. The height of the Eiffel Tower, according to this diagram, is 653.8 feet. All right. I think it's actually quite a bit taller than that, so my bad for not getting the right measurements. Oops. But the calculations, that's still how we would set it up. All right, here's a similar picture. This time it's not a mirror. This time it's a ball getting spiked. And when the ball hits the ground, it's going to leave the ground at the same angle. So still kind of the law of reflection going on here. Emma spikes the volleyball so that it bounces off the ground 4 feet away from her. So the distance from underneath her to where the ball hits the ground is 4 feet. Her hand was 5 feet off the ground. So she's smacking the ball from right here, which is 5 feet above the ground. The net is 6 feet beyond the position where the ball hit the ground. So from where the ball hit the ground to the edge of the net is 6 feet. And we are now trying to calculate the height of the net. So let's go ahead and have you do this one as well. right, let's see how you did. I can set up the height over the ground, so 5 over 4. And then I can do the height over the ground, x over 6. Cross multiply, that's 30, that's 4x, so 4x equals 30. Divide by 4, x equals 7.5. So the height of the net is 7.5 feet. So really, it's the same thing we did last week, right? We've got a picture of it. They tell us all the information. We just put the numbers where they go. We use what we know about proportions, and we solve. All right, I'm gonna do one more example. This one's a little trickier. So pay close attention on this one. There's one thing we gotta be careful about. So you, here you are, right? It says you. There's you. Are on one side of the creek, and your friend, here's your friend, is on the other side. Your friend is standing 5 feet beyond the edge of the creek, and you are standing 5 feet the other direction from the edge of the creek. We know that these triangles are similar because we're going to measure this distance here, which is 50 feet, and we measured that going at a 90-degree angle from the distance across. And then we also measured this, which is also at a 90-degree angle. So we have angle, and then we have these angles here, which we know are congruent because they are vertical. So we know we have similar triangles. And so now when I go to write my proportion, I might do something like 5 over 12. So in my triangle, that was the short side over the longer side, right? Not the hypotenuse though. So short leg over long leg. And so then if I go find the short leg of this triangle, I notice that I actually already have 5, right? Because my friend is standing 5 feet away from the shore, and that was part of that triangle. So what could I label this with right here? All right, that's the actual river, or the creek, and that's what I'm trying to find the length of. But I don't know that, so I'm just going to call that x. So x is the width of the creek. But if I want to label this whole side, right, because 5 was the whole side here, now I need to find the whole length of this side. Well, x is not the whole side, right? 5 is not the whole side, but together, if I add them, I do get that whole side. And then the 12 was my kind of longer leg, right? So that goes with this right here, 50 feet. And now we can go ahead and solve. 5 times 50, and then 12 times x plus 5. And just to make sure we're doing okay with this, go ahead and solve the rest of this equation. Okay, let's find out how you did. From here we have to distribute, which gives us 12x plus 60. And then we're going to subtract that 60 on both sides, which gives me 190 equals 12x. Divide by 12. Where did I put my calculator? There it is. All right. 190 divided by 12. And I got 15.833333. So I can say that the width of the creek is my x, which we found to be 15.833333 feet. Awesome. Similar triangles are pretty cool. All right, we'll go ahead and stop there for today. Definitely a little bit of a longer lesson, lots of examples for you to come back to if you need help on this stuff. But most of the rest of the week, we're just going to be practicing word problems and getting better at indirect measurement. So yeah, enjoy. Hopefully this will be a good week for you. Go Titans.